Welcome. In this video, we're going to be talking about something called the mole. When we look at a chemical equation, it tells us how many of each atom or molecule are needed for the reaction to happen. But when we're in the lab, we can only measure chemicals by their mass, how many grams we have, or the volume, how many milliliters they have. We can't actually count the number of particles in the sample. So that means we need a way to convert between the mass of the particles and the actual number or amount of the particles. This gets kind of messy because particles are really, really small. So it's almost as if you were building bicycles and you know a bicycle needs 2 tires per bike, but instead of knowing how many tires you have, you're told you have 100 pounds of tires. So how do you know how many bikes that can build? Well, you have to have a way to convert between your number of tires and your pounds of tires. That's the same thing we see going on in chemistry all the time, except tires are big enough to see and actually count. Particles, molecules, atoms, ions, electrons, all those different little chemical particles are so teeny tiny that we need a giant number. So Avogadro came up with a number that allowed us to convert from particles to mass or mass to particles, and it would be a big enough number that would actually have enough to see and measure and work with. So a mole is a chemical mass unit defined to be 6.02 times 10 to the 23rd molecules, atoms, or some other unit. So this is like a ginormous dozen. So the mole is just a counting number. Just like a dozen, you count 12 at a time. It counts the number of particles, not their mass or their volume. And it's a huge number, but it's still just a counting number. It's really what we call the chemist's dozen. So here's a mole written in scientific notation, and here it's written with all of its zeros. And you can see why we use scientific notation. So how big is a mole? Well, if you were counting normal size stuff, like a mole of marbles, it would cover the Earth to a depth of 50 miles. Or if you had a mole's worth of glasses of water, so 6.02 times 10 to the 23rd glasses of water, it would fill the Earth's ocean. If you had that many sheets of paper, you not only could form one stack of paper that would reach past the sun, you could form 1,000,000 stacks. And a mole of pennies could be divided among all the people of the world, and everyone could spend $1,000,000 per hour, every hour, day and night for the rest of their lives. So it's a ginormous number. But a mole of water molecules is only a little more than a teaspoon of water. So that means atoms and molecules are ridiculously small, and a mole of molecules is a ridiculously large number. So let's try a couple examples here. I like to use the same method every time because we're going to do a lot of conversions in the next few chapters. And what I like to do, my foolproof method or my no-think method, is to always look at what you have and what you want. So if I read the problem, it says how many moles are in 3.58 times 10 to the 23rd formula units. So what I have is, let me try that again, is 3.58 times 10 to the 23rd formula units. What's a formula unit? It's just what we call the particles in ionic compounds. Covalent compounds are called molecules. Ionic compounds or particles are called formula units. No big deal. What I want is moles. So I'm going to write down what I have or given, whichever way you want to think of it. 3.58 times 10 to the 23rd. I call these FUs, which some of you will be feeling that way after you do a few conversions. And now I have to set up a converter. And this is a little bit different than when you set up a ratio in math and you do the fish thing. You know, you have 2 ratios equal to each other. I'm setting up just one converter. I have 3.58 times 10 to the 23rd. I want to convert it to moles. So my converter is always going to be what I want over what I have. And what I know about moles and any kind of particle is 1 mole is always going to be 6.02 times 10 to the 23rd of whatever particles you're interested in, because that's what Avogadro defined it to be. So what I'm really deciding is whether or not I have to multiply or divide by that ginormous number. So in this case, I have to put Avogadro's number on the bottom, so I'm going to take 3.58 times 10 to the 23rd times 1 mole, divide by Avogadro's number. And when I do that, I'm going to get 0.595, and then my label is going to be moles because my formula units have canceled out and I've converted to moles, which is exactly what I wanted to do. And one thing to look and see is, does my answer make sense? And yeah, it does, because remember with exponents, you're really dividing 3.58 times 6.02, so that's around a half. 3 divided by 6 is about a half. And then 10 to the 23rd is being divided by 10 to the 23rd, which that should cancel out, which it does. So this seems like a reasonable answer. So let's try the second one. How many atoms are in 0.88 moles of copper? Remember, what do I have? That's the first thing I write down. The number I'm given, I write down. I never use that to make my converter. Then, what am I being asked to find? I'm being asked to change it to atoms. So now I have to set up my converter of what I want, atoms, over what I have from moles. And I use my converter up here. My 1 mole equals 6.02 times 10 to the 23rd. So this time, Avogadro's number goes on top. And you notice up here, I put it in parentheses to make sure I realize that's one number. I have to put that in parentheses when I put it in my calculator, or you get like 10 to the 47th or some ridiculous thing. On the top here, it's not as important to put it in parentheses because I'm just multiplying anyway. So it's up to you if you want to go ahead and bracket it. But when I take 0.88 times 6.02 times 10 to the 23rd, I'm going to get a little less than Avogadro's number. I'm going to get 2976, and I'm going to round to just 2 digits here, 5.3 times 10 to the 23rd. And again, my answer seems to be reasonable or to make sense. So here's a couple examples for you to try yourself. I would encourage you to pause the video here and see if you can solve these correctly by yourself. And I'll put the converter up here. 1 mole is 6.02 times 10 to the 23rd, whatevers. We'll say particles, whatever kind of chemical component you're talking about. So number 1, how many molecules are 1.35 moles? So there's what I have is 1.35 moles. And now I need to set up a converter. I'm being asked for molecules. I want molecules, I have moles. So that means the 6.02 times 10 to the 23rd goes on top. The 1 mole goes on the bottom. So 1.35 times 6.02 times 10 to the 23rd is going to be 8.13 times 10 to the 23rd. And then I need to label it molecules. How many moles are in 2.54 times 10 to the 15th? There's what I have, 2.54 times 10 to the 15th atoms of zinc. Doesn't matter what kind of atom it is, 1 mole is always 6.02 times 10 to the 23rd. So what I want is moles, what I have is atoms. 1 mole on top, 6.02 times 10 to the 23rd. Make sure that that's in parentheses and treat it as one number. So 2.54 times 10 to the 15th, isn't it going to be 1 mole? It's less than a mole. It's more than half, but it's definitely not a whole mole's worth. So I'm not expecting to get a number bigger than 1. So if I do, I know I've done something wrong in my calculating. So I end up with a whole bunch of zeros there, or if I tell my calculator to put it into scientific notation, which your calculator should be able to do for you, I come up with 4.22 times 10 to the minus 9th moles. And again, I was expecting to get less than 1 because 10 to the 15th divided by 10 to the 23rd is going to be around 10 to the minus 8th. So this seems like a reasonable answer.